bottom of the ocean is leaking black smoke. In total darkness, a stone chimney rises from the seafloor, pouring a black cloud into freezing water. But if there is no fire down there, what is making the smoke? There is a place on this planet where the ground breathes black. Not metaphorically, not poetically, literally. Right now, at this moment, somewhere beneath 2,000 meters of water, a tower of dark stone is exhaling. A thick, dark plume rises from its opening and spreads slowly into the surrounding ocean. It looks like a fire. It looks like something is burning. It looks like an industrial chimney seen from far away. Except there are no factories here. There are no cities. There is no light. There is no sound that human ears could hear without instruments. There is nothing, or so we once believed, but cold, crushing, eternal darkness. And yet the smoke keeps rising. It has been rising for thousands of years. No one saw it until 1977. For all of human history, every civilization, every sailor, every scientist who ever studied the ocean, this was happening and we had no idea. The seafloor was doing something extraordinary, and the ocean kept the secret effortlessly, because the ocean is very good at keeping secrets. When the first researchers descended in a small submarine called Alvin and saw what was down there, they didn't have the words for it immediately. They had theories. They had predictions about what deep ocean hydrothermal activity might look like. But seeing it, seeing the towers, seeing the black plumes, seeing what was living around them, was something their training had not quite prepared them for. One scientist reportedly said, "We should have brought more wine." That feels right somehow, because what they found that day was not just a geological curiosity, it was a crack in the worldview, a place where the rules seemed different, where life existed in conditions that life was not supposed to tolerate, where the planet itself was doing something strange and alive and ancient. The seafloor is leaking black smoke, and the more you understand what that means, the stranger it becomes. Let's slow down here, because the first thing to understand is also the most surprising. It is not smoke. What you see rising from the chimney, that thick, dark, billowing cloud, is not combustion. Nothing is burning. There is no fire in the geological sense, no rapid oxidation of organic material, no flame consuming anything. The word smoke is the word we reach for because it looks like smoke. It behaves like smoke. It rises like smoke through the water the way smoke rises through air. But it is something else entirely. It is water, or rather, it is superheated water saturated with minerals, a liquid so full of dissolved metals and sulfur compounds that when it meets the cold seawater above, those minerals instantly precipitate out of solution. They solidify. They become particles. And those particles, billions of them, each one invisibly small, are what make the plume dark. Think of it this way. If you dissolve sugar into hot water, the sugar disappears. You can't see it. But if you then pour that hot water into ice-cold water, the sugar can't stay dissolved. Some of it comes back out. You'd see it cloud and swirl in the colder liquid. What happens at a hydrothermal vent is something like that. But instead of sugar, the dissolved substance is iron sulfide. And instead of turning white or cloudy, iron sulfide turns black. So the smoke is not smoke. It is a mineral storm in miniature, happening continuously, in real time, in total darkness, 2 kilometers below the surface of the sea. The chimney is not burning. The chimney is crystallizing. And it has been doing this, quietly and without any witness, for longer than our species has existed. To understand why this happens at all, you have to go deeper. Not into the ocean, into the planet itself. The Earth's surface is not one solid piece. You know this probably. You learned it somewhere. School, a documentary, a late-night thought about earthquakes. The crust is divided into plates, enormous sections of rock that float on the semi-molten material beneath them. These plates move. slowly, at roughly the speed your fingernails grow, but they move. And they have been moving for billions of years. In some places, two plates push against each other. Mountains rise, volcanoes form. In other places, two plates slide past each other. Earthquakes happen along the fault lines. But there is a third possibility, and this is the one that matters for what we are watching on the seafloor. In some places, two plates pull apart. When oceanic plates pull apart from each other, they leave a gap, a rift. The Earth's interior tries to fill that gap, and the way it does this is by pushing magma, molten rock, up from below. This creates what scientists call a mid-ocean ridge, a mountain range that runs along the ocean floor, marking the boundary between plates. The Mid-Atlantic Ridge, the East Pacific Rise, the Central Indian Ridge. There are thousands of kilometers of these underwater mountain ranges, most of them never seen by human eyes. And along these ridges, the planet's interior is perpetually close to the surface. The crust is thin here. The rock is relatively young, and the heat from below is significant. It is along these ridges, at these seams in the planet's skin, that hydrothermal vents form. The Earth is cracked, and through those cracks it breathes. Here is where the ocean and the planet begin to work together. The seafloor is not perfectly solid. There are cracks and fissures in the oceanic crust, especially near those mid-ocean ridges where the rock is youngest and still forming. These are not dramatic chasms you could peer into. They are often small, narrow fractures, gaps in the rock measured in millimeters or centimeters rather than meters. But seawater is patient, and it is persistent, and it finds its way in. Cold seawater, just a few degrees above freezing, dense and heavy, seeps down through these cracks. It follows the fractures in the rock, descending slowly through the crust, down through the basalt, down through layers of stone that have never been touched by sunlight, that exist in a darkness even more complete than the darkness of the deep ocean above. The water moves slowly. There is no rushing here. This is geological time, not human time. But it moves, and it goes deeper. And as it goes deeper, the temperature rises. The Earth's interior is hot. We know this because volcanoes exist, because lava flows across the surface in some places, because if you drill far enough into any piece of ground on this planet, you will eventually reach temperatures that no living thing could survive. The deeper you go, the hotter it gets. And so the seawater, descending through the cracks, is moving toward heat. At first, the change is gradual. The water warms slightly, then more. It begins to dissolve minerals from the surrounding rock. It strips away silicates and sulfates and metals, iron, copper, zinc, manganese, pulling them out of the solid stone and carrying them in solution. The water is becoming something different from what it was. It entered as cold, relatively pure seawater. Now it is becoming a chemical broth, a mineral-rich fluid that carries the signature of the rock it has passed through. It descends, it heats, it collects, and then it turns around. There is a moment, deep in the crust, close to where the magma is not far beneath, when the water cannot descend any further. The heat becomes too intense. The fluid reaches temperatures that, under normal circumstances, would cause it to boil violently. But it doesn't boil. This is one of the stranger facts about hydrothermal vents, and it matters. The water does not boil, even though it reaches temperatures above 400 degrees Celsius, far above the boiling point of water at sea level, far above any temperature you have ever cooked with, or bathed in, or felt in any form. The reason it doesn't boil is the pressure. At 2,000 meters below the ocean surface, the weight of all that water above creates a pressure roughly 200 times greater than what you experience on land. And pressure changes the properties of water in a fundamental way. It raises the boiling point. The more pressure there is, the hotter water can get before it transitions to steam. So the fluid in the crust exists in a strange state. It is hotter than boiling, but it doesn't boil. It becomes what physicists call a supercritical fluid. Not quite a liquid, not quite a gas, something in between, with properties of both. It is extraordinarily chemically reactive in this state. It strips minerals from the surrounding rock with even greater efficiency. And then, because hot fluid rises, because heat always wants to go up, it begins its journey back. The superheated fluid, loaded with dissolved minerals, reverses direction. It finds pathways through the rock, moving upward now, following the same cracks and fractures it descended through, or finding new ones. It rises toward the seafloor, carrying everything it has collected from the deep. As it rises, the pressure decreases slightly. The temperature in the surrounding rock is lower. The fluid is still extraordinarily hot, but the chemistry is changing, and the clock is ticking. It is heading for the cold. When the superheated fluid finally reaches the seafloor and emerges into open water, the change is immediate and violent. The fluid may be 400 degrees Celsius. The surrounding seawater is perhaps 2 degrees. The difference is almost 400 degrees, happening within centimeters, within fractions of a second. The minerals that were held in solution dissolved because the water was hot enough and the pressure was right, can no longer stay dissolved. They come out of solution instantly. They solidify. Crystals form on any available surface. Metal sulfides precipitate in the water column, creating those dark particles that make the plume look like smoke. And they also build. Over time, over years, over decades, over centuries, the minerals accumulating around the vent opening form structures. Layer by layer, crystal by crystal, the minerals stack up. They form walls. Those walls grow upward. What begins as a simple opening in the seafloor gradually becomes a tube, then a chimney, then a tower. Some of these chimneys are small, barely a meter tall, just a modest pipe rising from the sediment. Others are extraordinary. Structures 10 meters tall, 20 meters, rising from the seafloor like cathedral spires. One structure discovered at a site in the Pacific became famous among deep-sea researchers. It stood taller than a 15-story building. These are not fast-growing structures by human standards, but they are not always slow either. Some hydrothermal chimneys grow at rates of 30 centimeters or more per day under the right conditions. A structure that didn't exist when you went to sleep might be taller than you are by the time you wake up. They grow in absolute darkness. They grow in crushing pressure. They grow in water so cold that it would kill a person in minutes if they were somehow transported there. And they are beautiful. The shapes are irregular, branching sometimes, clustered, sometimes solitary and spire-like. They are made of layered minerals, iron sulfides, zinc sulfides, copper compounds, that give them colors you would not expect in a dark place. Black, yes, but also rust red, pale yellow, golden brown. Colors that no sunlight will ever illuminate. Colors that exist only for the instruments of the scientists who find them. We can answer the question now. The smoke is black because of iron sulfide. When the superheated fluid rises and meets cold seawater, one of the first things to precipitate, to come out of solution and form solid particles, is iron sulfide. This mineral, sometimes called pyrrhotite, or related to the mineral pyrite that you might know as fool's gold, forms in extremely fine particles when it precipitates rapidly. Those particles are black. Not dark brown, not dark gray. Black. In the way that powdered charcoal is black. In the way that something absorbs rather than reflects light. Billions of these black iron sulfide particles form in the plume every second, and they are what give the black smoker its name and its dramatic appearance. The plume is dense with them. When the current is low and the vent is vigorous, they can form a column that rises 50 meters, 100 meters above the chimney opening, before diffusing into the broader ocean. The particles eventually settle. Some of them drift for kilometers before landing on the seafloor, creating a faint, dark sediment that records the presence of the vent in the geological record. Geologists can sometimes identify ancient vent fields, ones that have been inactive for millions of years, by finding these sediment signatures. So the plume is black because the minerals in the fluid are primarily iron sulfide compounds. Different chemistry produces different colors. White smokers, which we will return to later, produce pale plumes because their fluid is dominated by other minerals: barium, calcium, silicon compounds that are white or pale when they precipitate. The color of the smoke tells you what the Earth is made of right there, in that specific place. Black means iron. Black means sulfur. Black means the deep interior of the planet, exhaled. There is something worth sitting with here before we move on. There is no fire down there. Nothing is burning. There is no combustion, no flame, no oxygen being consumed in rapid oxidation. And yet, by any sensible definition of the word, this place has energy. It has enormous energy. The fluid emerging from an active black smoker carries as much thermal energy as some industrial furnaces. The temperature differential between the vent fluid and the surrounding water is large enough that, in principle, you could use it to generate electricity. The Earth is releasing energy here, not through burning, but through the simple fact of its own internal heat. The planet is old, and its interior is still cooling from the violence of its formation 4.5 billion years ago, and from the ongoing radioactive decay of elements deep in its core and mantle. That internal heat has to go somewhere. Some of it escapes through volcanoes. Some of it seeps slowly through the crust everywhere on the planet. And some of it, a significant fraction, escapes through the seafloor at hydrothermal vents. The ocean is not just sitting on top of the planet. The planet and the ocean are in constant conversation. Heat flows upward. Water flows downward. The chemistry of the seafloor fluid is shaped by both the ocean's composition and the crust's composition. The ocean, over geological time, has been partly shaped by what the vents release into it. There is an energy source down here that has nothing to do with the sun, a fire without flame, a warmth without light, an energy system that has been running since the oceans formed, independent of photosynthesis, independent of surface conditions, operating in the dark by its own logic. And life found it. This is the part that changes things. We were taught, most of us, that life on Earth depends on the sun. This is a reasonable thing to teach. It is, in broad terms, true. The great food webs of the world's ecosystems trace back ultimately to photosynthesis. Plants, algae, phytoplankton, organisms that capture sunlight and use it to build sugars from carbon dioxide. Those organisms feed everything else. The sun is the foundation. But here, at the hydrothermal vents, there is no sunlight. Sunlight penetrates the ocean only so far. Below about 200 meters, it is too dim to support photosynthesis. Below 1,000 meters, there is essentially none. At 2,000 meters, where many hydrothermal vents are found, the darkness is complete. No photon from the sun has ever reached this place. And yet, life thrives here. The discovery of vent ecosystems in 1977 required a genuine rethinking of what biology was capable of. The scientists who saw the creatures clustered around those first vents were astonished, not just because life existed in extreme conditions, but because it existed in such abundance. There were dense clusters of organisms in a place that, by the logic of previous biology, should have been nearly lifeless. How? The answer was a form of metabolism called chemosynthesis. Photosynthesis uses light energy to convert carbon dioxide into organic matter. Chemosynthesis does the same thing, converts inorganic carbon into organic compounds, builds the sugars and proteins that form the foundation of life. But it uses chemical energy instead of light energy. The chemical energy available at hydrothermal vents is substantial. The reduced sulfur compounds in the vent fluid, hydrogen sulfide in particular, represent stored energy. When hydrogen sulfide is oxidized, energy is released. Certain microorganisms have evolved to capture that energy and use it to drive their metabolism. These microorganisms, bacteria and archaea, are the base of the vent food web. They are the thing that replaces the sun. In the darkness, at the chimney's edge, billions of microbes process the chemistry of the vent fluid and extract energy from it. They build their bodies from carbon. They multiply. They form the foundation on which everything else that lives here depends. The logic is the same as photosynthesis. The source of energy is different, and this matters enormously, not just for understanding life on Earth, but for understanding what life might be capable of anywhere in the universe. Let's stay with the microbes for a moment. They are easy to overlook because they are invisible, because they are ancient, because they have no faces or behaviors that we naturally find interesting. But at the hydrothermal vent, they are everything. They are the reason anything else exists here. Some of them live freely in the water around the vent, suspended in the plume, processing the chemicals that pass through them. Others form thick mats on the surfaces of the chimneys and the surrounding rock. Dense, layered communities that can look, from a distance, like orange or white or tan fur coating the stone. These mats are, in a real sense, the pasture of the deep ocean vent ecosystem. Many vent animals graze on them directly, but the most interesting microbial relationship at hydrothermal vents is one of partnership. Many of the larger, more visible vent animals, the ones we will talk about in a moment, do not eat in the traditional sense. They do not have mouths in some cases. They do not consume other organisms. Instead, they have evolved a relationship with chemosynthetic bacteria that live inside their bodies. The bacteria live within the tissues of the animal. The animal provides the bacteria with access to the chemicals they need: hydrogen sulfide from the vent, oxygen from the surrounding seawater. The bacteria process these chemicals and generate organic compounds as a byproduct. The animal absorbs those compounds as nutrition. Neither organism could survive without the other. The animal is a living habitat for the bacteria. The bacteria is a living food source for the animal. This kind of arrangement, where two organisms of different species live in such close association that the boundaries between them become blurry, is called endosymbiosis. And it is not unique to hydrothermal vents. The mitochondria inside your cells, the structures that produce energy for every process in your body, are thought to be descended from ancient bacteria that entered into an endosymbiotic relationship with our single-celled ancestors more than 1 billion years ago. In a sense, the relationships you see at hydrothermal vents are a living echo of the deepest history of complex life. The microbes that feed a world are not so different from the microbes that, long ago, helped build us. Now we can look at what lives here. The first thing you notice, if you are watching footage from a deep-sea submersible approaching an active hydrothermal vent field, is that it does not look empty. It looks crowded. It looks, impossibly, given everything you know about the deep ocean, full. Tube worms are often the most dramatic sight. Riftia pachyptilla, the giant tube worm, can grow to more than 2 meters in length. Each one lives inside a white tube of its own making, with a bright red plume extending from the opening. The plume is an organ for gas exchange, rich with hemoglobin, which is why it is red. The worms have no mouth, no stomach, no digestive system in the conventional sense. Their entire nutrition comes from the chemosynthetic bacteria living inside a specialized organ in their bodies. They cluster around the vents in dense communities. Hundreds of them, sometimes thousands, their red plumes waving slowly in the current created by the rising vent fluid. From a distance, a colony of tube worms looks like a field of strange flowers, or a thicket of some alien plant life, swaying in a wind that is actually superheated mineral water. Around and among the tube worms, other creatures move. Vent mussels and clams attach to the rock surfaces, their shells sometimes massed so densely that they form continuous layers. Like the tube worms, many of these bivalves have chemosynthetic bacteria in their gills. They filter some food from the water, but their primary nutrition comes from within. Vent shrimp swarm in numbers that can seem almost frantic, pale, eyeless, or nearly eyeless, moving constantly. Some vent shrimp have modified sensory organs on their backs that are thought to detect the faint glow of the vent fluid itself, a kind of light that exists not from photons, but from the thermal emission of superheated material. They are navigating a world of chemistry and heat, not light. Crabs move through the scene with the unhurried deliberateness of things that know there are no predators here large enough to trouble them. Some are covered in what look like fine hairs, actually filaments that harbor chemosynthetic bacteria, turning the crab's own body into a kind of farm. Fish appear occasionally, drawn by the abundance of prey. White octopus drift through. Various species of polychaete worms, relatives of the earthworm, but adapted to conditions that make the deep ocean seem mild, live in the hot zone itself, closer to the vent opening than most creatures can tolerate. And the snail, Chrysomalon squamiferum, known informally as the scaly-foot snail, is perhaps the most remarkable creature associated with hydrothermal vents. It wears a shell armored with iron sulfide scales. Literally, it incorporates the minerals of the vent into its own body armor. It is the only animal known to use iron minerals as part of its defensive structure. It is, in a very direct sense, a creature that is made partly of the same material as the black smoker chimney itself. Let's name what is in that water: hydrogen sulfide, the compound that gives rotten eggs their smell, toxic to humans. It disrupts the same oxygen-carrying mechanisms in our blood that cyanide does. In high concentrations, it kills quickly. Heavy metals: iron, copper, zinc, lead, sometimes arsenic. The kind of chemical soup that, if you found it in a river or a well, would mark it as severely contaminated and dangerous to approach. Extreme heat: the fluid emerging from the vent itself at temperatures that would cook human tissue in seconds. The mixing zone around the chimney, where hot vent fluid encounters cold seawater, produces a gradient of temperatures, from near freezing to several hundred degrees, across distances sometimes measured in centimeters. Extreme pressure: 200 atmospheres or more, enough to crush a human body, and the submersibles that carry scientists to these depths are engineered precisely to withstand this, with hulls of titanium or high-strength steel, tested to survive the equivalent of millions of kilograms pressing on every surface. Darkness: complete, absolute, unrelenting. No day cycle, no seasonal change in light. Nothing that any surface organism has evolved to navigate by. And yet, the tube worms thrive in the mixing zone, their root-like anchors reaching toward the hottest parts of the vent, where mineral-rich fluid is most concentrated. The vent shrimp swarm through water that carries hydrogen sulfide at concentrations that would be immediately dangerous to breathe. The bacteria that form the base of the ecosystem process hydrogen sulfide as fuel. They don't tolerate it, they need it. There are microorganisms found at hydrothermal vents, hyperthermophiles, organisms that love extreme heat, that have optimum growth temperatures above 80 or 90 degrees Celsius. Some can survive and reproduce at temperatures close to the boiling point of water at sea level. These organisms, if placed in the temperature conditions we consider comfortable, would effectively freeze. They are not tolerating their environment. This is their environment. The conditions that would kill us in minutes are the conditions that this ecosystem was built for, that evolution has been refining here for, by some estimates, billions of years. What we see as hostile, they have never experienced as anything other than home. This is an important thing to sit with because it changes the meaning of the word extreme. Extreme from whose perspective? Not all hydrothermal vents are alike. The black smokers are the dramatic ones, the high-temperature vents that produce those dark, billowing plumes. Their fluid is typically above 300 degrees Celsius, sometimes well above 400. The chemistry is dominated by iron and sulfide compounds. The plume is dark because iron sulfide particles form immediately when the hot fluid meets cold water. But there are other kinds. White smokers are different in fundamental ways. Their fluid is typically cooler, sometimes still quite hot by any human standard, but lower temperature than black smokers. And the chemistry is different. White smokers produce fluids rich in barium, calcium, and silicon compounds. These minerals are white or pale when they precipitate, and so the plume they create is white or gray rather than black. There is a structure that may be the most famous hydrothermal feature ever discovered, a field called Lost City, found in 2000 in the Atlantic Ocean. Lost City is not a typical hydrothermal vent system. Its chemistry is driven not by proximity to magma, but by a geological reaction called serpentinization, in which water reacts with certain types of rock and produces heat as a byproduct. The result is a forest of white carbonate towers, some of them 60 meters tall, that have been active for tens of thousands of years. The fluid is highly alkaline, very different in chemistry from the acidic black smoker fluid. Lost City has its own ecosystem, its own community of microbes and animals. A different world from the black smoker world, operating by related but distinct rules. The variety within what we call hydrothermal vent systems is itself remarkable. Each vent field has its own geological context, its own chemistry, its own temperature regime, its own community of inhabitants. The deep ocean is not one place. It is many places, each shaped by the specific crack in the planet that created it. There is an economic dimension to hydrothermal vents that has become increasingly significant. The minerals deposited by vent activity are not random. They are often the same minerals that human civilizations have mined and valued for thousands of years. Copper, zinc, gold, silver, cobalt, and rare earth elements that have become important for modern electronics and batteries. Over the lifetime of an active vent, the accumulation of these minerals can be substantial. Massive sulfide deposits, the geological term for the mineral accumulations that form around hydrothermal vents, have been found on the seafloor in sizes and concentrations that would be considered significant ore deposits if they were on land. Some of these deposits are relics of ancient vent activity, structures that were once black smokers, perhaps millions of years ago, and have since gone cold. The minerals remain. They sit on the seafloor, enormous mounds of metal-rich rock, marking the places where the earth once exhaled. Others are actively forming right now. The minerals being deposited by active vents include the same metals that contemporary industry needs in increasing quantities. This has led to a significant and genuinely complex conversation about deep-sea mining. The potential to extract these minerals is real. The technology to do so is being developed. Several nations and private companies have explored, mapped, and in some cases, obtained exploration licenses for areas of the seafloor that contain hydrothermal mineral deposits. But the ecosystems around these vents are unique. They are irreplaceable in the sense that each vent community develops over decades or centuries and has species compositions that may exist nowhere else on Earth. Some of the species have not even been cataloged yet. Scientists estimate that many vent species remain undiscovered. The ecological cost of mining would be significant. This tension between the minerals the world below offers and the life it has quietly built over millennia is one of the genuinely unresolved questions that hydrothermal vent research sits inside. There are no easy answers. There is only the weight of the choice and the darkness in which it would be made. Here is the biggest question. Some scientists think that life on Earth may have begun at hydrothermal vents. This is not the consensus position. There is no consensus position on the origin of life, because we don't have enough evidence yet to be certain about anything. But the hydrothermal vent hypothesis is a serious scientific proposal developed by researchers over several decades, and it deserves to be treated seriously. The basic argument is this: the first living organisms needed, at minimum, a source of energy, a source of chemical building blocks, and some kind of physical environment where chemistry could concentrate and organize itself. Hydrothermal vents, particularly alkaline vents like Lost City, provide all three. The energy comes from the chemistry, the same chemosynthetic reactions that power today's vent ecosystems were available on early Earth. The chemical building blocks, carbon compounds, nitrogen, sulfur, phosphorus, are all present in vent fluid, and the physical structure of the vent chimney itself, with its porous, interconnected chambers of minerals, has been proposed as a kind of natural reactor, a place where chemical reactions could concentrate and build complexity. Some researchers have noted that the chemistry of alkaline hydrothermal vent fluid is in certain ways similar to the chemistry inside living cells. The gradient between the alkaline vent fluid and the more acidic early ocean is similar to the proton gradient that living cells use to generate energy today. This is striking enough that it has generated significant research and debate. We don't know if this is where life began. The evidence is not there yet to be certain, but the possibility is real enough that it shapes how scientists think about other questions, particularly the question of whether life might exist elsewhere in the solar system. Europa, a moon of Jupiter, is believed to have a global ocean of liquid water beneath its icy surface. That ocean is kept liquid by the tidal forces of Jupiter's gravity, which heat Europa's interior. If Europa's seafloor experiences tectonic activity, there may be hydrothermal vents there. And if there are hydrothermal vents, the same chemistry that supports life in Earth's deep ocean might be occurring right now, in the dark beneath Europa's ice, around chimneys that no one has ever seen. The same logic applies to Enceladus, a moon of Saturn, which has been observed actively venting material from its subsurface ocean into space, material that includes hydrogen gas, a signature of the same serpentinization reactions that drive some hydrothermal activity on Earth. What we learn from black smokers on Earth is not just about Earth. It is about what is possible anywhere a planet is warm and wet. Here is where we end. Right now, as you listen to this, the ocean floor is doing what it has done for longer than complex life has existed on this planet. The water is seeping through the cracks. The Earth is heating it. The superheated fluid is rising, laden with minerals, carrying the chemistry of the deep interior back toward the surface. The chimneys are building themselves, stone by stone, crystal by crystal, in total darkness. The bacteria are processing sulfide into energy. The tube worms are waving their red plumes. The vent shrimp are swarming through the hot zone. The scaly-foot snail, armored in iron, is moving slowly across mineral-crusted rock at the base of a chimney that has been growing for 200 years. None of it knows it is in darkness. None of it needs the sun. The planet is not dead below us. The interior is not silent. The ocean floor is not an empty wasteland at the bottom of a cold, featureless abyss. It is, has always been, alive, active, breathing. The mid-ocean ridges stretch for 60,000 kilometers across the seafloor, the longest mountain range on Earth, mostly unseen. Along those ridges, hundreds of hydrothermal vent fields have been identified. Scientists estimate that there may be thousands more yet to be found. Each one a small window into the planet's interior. Each one a community of life that has been there, in its darkness, long before we had words for it. We have been on this planet for a few 100,000 years. The vents have been there for billions. In all that time, through the mass extinctions that wiped out most complex life on the surface, through the ice ages, through the changes in ocean chemistry and atmospheric composition that would have been catastrophic for surface ecosystems, The deep-sea vent communities persisted. They did not care what was happening above. They were operating on a different energy system, connected to a different source, insulated by 2 kilometers of water from whatever calamities reorganized the surface world. There is something quietly steadying about this. In a world that feels unstable, there is a place that has been stable for geological time. Not safe by our standards, not warm, not lit, not welcoming in any surface creature sense, but stable, continuous, alive by its own rules, for its own reasons, in its own darkness. The seafloor is leaking black smoke. It has always been leaking black smoke. And at the base of those chimneys, in water that would kill us before we understood what was happening, the earth has quietly been sustaining something extraordinary, life, in conditions we thought impossible, around heat that comes from no star but our own planet, operating in a darkness as complete as any that exists, and thriving. Sleep now. The deep ocean is doing what it has always done, and the earth is still breathing below.